All right, hey guys. I'm gonna go ahead and put up a warm up here. Oops. Let's see. So, well, I don't know. I'll just make little bullet points or something. So tangent of x on 0 pi over 4. And x sine squared x on 0 pi 1 over x minus 3 on 1 over x minus 3 on 3 infinity. And I'm going to go ahead and throw in, let's say, sine of 1 over x on a infinity, where a is greater than 0. So yeah, just, and try to justify your answers. Obviously don't waste time, writing down big, long proofs or anything, but just think about like, what theorem would I invoke to justify, or like in a sentence or two, like how would I explain why I believe what I believe? So yeah, let's say we'll resume at, I don't know, 5:15. All right. Okay, so let's just go through these pretty quick here. So for the first one, right, tangent of x is just continuous on 0 pi over 4. If you want, you can think of it, I mean, well, I don't know. You have to take for granted that, sine of x and cosine of x are continuous everywhere. So as long as we assume that much, sorry, maybe I should have sort of said that, like, assume sine of x, cosine of x are continuous everywhere. But I mean, that's just going to be like a working assumption for pretty much the entire class, because we don't actually define the functions sine and cosine in the class. So it's like there isn't really a way to prove that they're continuous from definitions. So anyway, yeah. So as long as those are continuous, then that implies that tangent of x is continuous wherever cosine of x is not 0, right? That's or wait. Yeah. So that's enough to say that that tangent of x is continuous on this interval, right? And so because it's continuous, it's automatically uniformly continuous, right? That's by what was it, 19.2 or something. Yeah. So, and then here, this one is not uniformly continuous. How would you justify this? Does anyone know? Like, quickly, don't go through like a whole, epsilon delta argument or anything. There's pretty much a one sentence like justification. Does anyone have it? Actually, one second. Let me bring up the participants. All right. Yeah, does anyone know? Well, okay. So since tangent of x, well, actually, the easiest thing to say really is that if you take, take a sequence, let's say xn going to pi over 2, right? Then it's easy to show that tangent of xn goes to infinity, right? And with xn, like, let's say xn less than, or less than pi over 2, right? Right. Tangent of xn goes to infinity just because sine of xn goes to 1 and cosine of xn goes to 0, right? And it's, both sine and cosine are positive. So tangent of xn goes to positive infinity. And that means that the sequence tangent of xn is not Cauchy, right? So then by 19.4, I think. Yeah. So 19.4 says that this can't be uniformly continuous. Sorry, it's getting a little bit cluttered. Let me like switch colors or something. So this is one thing. And then this is another thing. Okay. Okay, I'll keep writing in red. So, okay, 1 over x sine squared of x. This one is uniformly continuous. And this basically, you kind of, I guess, yeah, it's a little bit hard to like be really rigorous about this, but we can extend, yeah, I don't know. We can extend 1 over x sine squared of x to 0 pi by defining the value at 0 to be 0. Okay, so the limit as x approaches 0 of this expression is 0. And yeah, I guess I don't know if we really have a way of actually showing that that's true. I guess if you could take for granted at least that sine of x is less than or equal to x for, you know, positive values of x, then you know, this becomes, the absolute value here becomes less than or equal to x. So then you can just show that that approaches 0. Or if you want, you could use like L'Hopital's rule, which we totally haven't proved or anything. But yeah, this is all meant to just be kind of like heuristic analysis. So it's not, you know, it's more about like seeing the reasons why something's true, even if we haven't like really proved them yet, I guess. And trying, but also like trying to use the theorems that we have developed so far. So this extension thing is totally like what you want to think about here for this one. The fact that we can extend it to 0 continuously is key. And then here, this one is not uniformly continuous. This is similar to the second one, right? Because it approaches, you know, I guess it approaches negative infinity as x approaches 3 from the left, right? So you can take a sequence approaching 3, then the values of the function on the sequence approach negative infinity. So the original sequence is Cauchy, but the values of the function are not Cauchy. So that's bad. And then also not uniformly continuous, similar to the previous and the second ones. And then this one is uniformly continuous, right? And one way of seeing this would be, you know, the derivative is bounded for one thing, or, you know, actually, I think that's probably like the only really concise way of arguing that it is. Yeah. Otherwise, you kind of have to do the whole like epsilon delta thing. But, you know, it's not too hard because, again, it's a situation where it's just like, you know, you can get some easy upper bound on, you know, absolute value of f of x minus absolute value of f of y by considering like the behavior near x and y equal 4, basically. And then this one is uniformly continuous as well. And another way, I think you can say, yeah, the derivative is bounded here too. So, yeah. Actually, I guess this is kind of like that. Something like that. Okay. Anyway. So any questions about this? I hope all of you could at least sort of tell which ones you expected to be uniformly continuous and which ones you don't expect to be uniformly continuous. Or which ones you expect not to be, right? Because that's kind of...
Can I ask a question?
Sure, yeah.
What's the difference if you set the second one like to like closed set, like when you, I mean like from 0 to pi over 2, right? It's open at the right side, but what if it's closed?
Well, the problem is that tangent of x is not defined for x equals pi over 2.
Uh-huh.
So, you know, I mean, I think it's just a basic requirement for uniform continuity that like the function has to be defined on the entire set.
Okay.
Yeah. Any other questions?
I have a question.
I accidentally had a closed bracket here at first, and I changed it. So yeah. Sorry, go ahead.
Can I have something? Are there any examples where it's like not what you expect?
Hmm. Well, it's hard to say because it's like it's hard for me to like to know what might be surprising, I guess. I mean, I don't know. I think part of the problem is that I'm sort of like too used to this idea now, so I can't think of any like really good ones that are like really surprising, I guess. Right off the top of my head, I can't really. Um I mean, I guess like things can get really weird if you start to let the set in consideration be anything that isn't just like a simple interval. Like if you let S become like a really strange set, then I'm sure some pretty messed up stuff can happen, but like I don't off the top of my head, it's like really hard to generate like truly interesting examples of that. Um, so yeah, I feel like these examples here honestly cover most of most of the types of behavior that you should really be familiar with, to be honest. um, because we have stuff that's sort of like infinitely oscillating near a point, or stuff that's you know uh, like has a pole at a point or something, or um, oh wait, oh yeah, yeah, yeah. Or stuff that can like, yeah, I mean, I don't know, yeah. I think most of the, I think maybe also the example of something like x sine of 1 over x is a pretty interesting one, just because that one does oscillate an infinite amount of times as you get close to zero, but since the amplitude also goes to zero, it ends up being uniformly continuous. Um, so yeah, this one you could argue is kind of like a mildly surprising example, maybe. I don't know. But yeah, I can't think of many that are like that much more exotic than this, at least not at the moment. Any other questions? Yeah, it's just really important to remember that uniform continuity depends just as much on the function as on the set that you're looking at, basically. Yeah. And that it changes. And that also, like, I think it's always sort of hard for people to really get used to the idea that, like, something like this could be true for an arbitrary value of a greater than zero, but then as soon as a equals zero, this becomes like false, that it's not uniformly continuous anymore. So it's just like reaching that point like causes this problem, but you can get arbitrarily close to it and then everything's fine. um, yeah, and it's just because like the delta that you pick that works on a infinity depends on like on the interval from a to infinity. The delta you pick kind of depends on a, and it's forced to depend on a, and as a gets closer and closer to zero, then the delta will also get closer and closer to zero, but you're not allowed to pick delta equals zero. So that's kind of the problem, I guess. But yeah, anyway, okay, so if there are no other questions, then I figure I'll go ahead and put up another exercise, and this can be one that you guys can work on together. So I thought this one is pretty good. So yeah, let's say, sure. So yeah, let's do this. So let f be continuous on 0 infinity. This is a closed bracket. Prove f. Yeah, prove that if f is uniformly continuous on k infinity for some k, then f is uniformly continuous on 0 infinity. Okay, so yeah, you want to do this carefully, of course. Give a fully rigorous proof here. So since there are, it looks like 6 of you, I'll go ahead and make 2 little rooms here. There we go. All right, so yeah, let's say, oops, we can resume at 5:40. All right. So let's see. Would anyone like to kind of describe like sort of the basic, like the outline of your approach to showing this?
I think like informally, it makes sense that the interval 0 to k has some like finite, I don't know, like what do you call it, like length of delta that would work
Hmm.
for epsilon.
Yeah. That's right. Yeah.
And then like I think you like take like the minimum of that delta and whatever the delta on the other interval.
Yeah. So that's like absolutely the correct like insight. I mean, that's the correct principle here, is that like f is like automatically well behaved on 0k, or indeed any 0 whatever, I don't know, a, right? Because they're closed intervals and f is continuous, right? So you can kind of find like the smallest delta you need across this entire interval, and then we're also given that it is well behaved for k infinity, right? The only technical issue, so technical problem, right, is if we choose delta is like the minimum of like delta 1 and delta 2, where this one is for like 0k and then this one's for k infinity, then we don't know how to bound f of x minus f of y if like x is in 0k and y is in k infinity. That's a slight problem, but so there's sort of a trick. Dang it. Oh, there we go. Whatever. There's sort of a trick to get around this, which is, I kind of hinted at it here, right? Which is that you can actually take advantage of, we know a lot more than just that like f is uniformly continuous on 0k. So you can actually just like adjust this slightly, like you could take 0k plus 1, for example. So, you could say like, so like let epsilon be greater than 0, right? F is uniformly continuous on 0k plus 1 means there exists a delta 1 such that, for all x, y in 0k plus 1, yada, yada, right? And then f is uniformly continuous on k infinity means there exists a delta 2 such that for all x, y in k infinity, yada, yada, right? So then take delta equals, how should we choose delta? It's not actually just the minimum of delta 1 and delta 2. There's one more trick. Okay, so the problem is if we just take delta 1 and delta 2, like if delta 1 and delta 2 are really big, we might still have like, we might accidentally get x. X might be between 0 and k, and then y might be between k plus 1 and infinity. So they might be further, they might not be in the overlap, basically, is the problem. So we have to take delta to be like the minimum of like 1, delta 1, and delta 2. Right. So then for x, y in 0, infinity with x minus y less than delta, we have either both x and y are in 0, k plus 1, or both x and y are in k infinity, right? So that's kind of the the trick. I think I did that right. What do you think?
Can you explain the part about the picking the delta again?
Oh yeah, so like the reason, okay, so we obviously we want to do minimum of delta 1 and delta 2 just so that like you know, whichever of these two sets the pair xy ends up in, we know that they're closer than the corresponding delta for that set. So we know that like f of x minus f of y is going to be closer than epsilon, basically, right? So that's the reason there's the delta 1 and delta 2 here. But then we also pick this 1 so that we can actually say, like, if x minus y are closer, if x and y are closer than delta, then they actually both have to be either they're both in this set or they're both in this set. Like, if we don't make them be less than 1 apart from each other, if like x minus y is greater than 1, then it's possible x is in like 0, k, like that, let's say, and y is in k plus 1 infinity, which would be bad because then we wouldn't be able to invoke like we wouldn't be able to like invoke what we know about our choice of delta 1 and delta 2, basically. Because delta 1 only guarantees that for two elements of 0, k plus 1, right? Like 2 points in this set, delta 1, the distance of delta 1 will guarantee that the values of the function are within epsilon of each other, right? But if one of them is in the other set, then we don't know anything about like whether they're within epsilon of each other because, you know, we chose delta 1 for the set 0, k plus 1 specifically, right? And delta 2 is for the set k to infinity. So like we basically just can't say anything about f of x minus f of y if one of them is in this set and the other one is, or like if they're not both in one of these two sets, basically, right? Like if they're not both contained in at least one of these two sets, then that's a problem. So the 1 basically just forces them to be, right? And it's because we put the k plus 1 here, right? Like if you put k plus 2, then you'd change this to a 2, right? Or literally if you put, you know, k plus, you know, plus a for any a greater than 0, you'd put a here, right? So that way, that forces it to be the case that either they're both in 0, k plus a, or they're both in k infinity. Okay? Does that make
Okay.
sense?
Yes.
Okay. Great. So we have a little bit of time left. Actually, well, before I try to give another exercise, which I'm not sure we really have time for, if you guys have any generic questions about, you know, anything so far, you know, I'm happy to answer any questions now.
You know what I would find helpful, if you're up for it, is like an extra video or maybe like comments during the video that about like going from like kind of your idea or like outline of the proof to like a like type formal proof.
Yeah, maybe I might be able to do something like that. I was thinking about um trying to make a video about like good writing practices. Um but it was going to be more about like kind of admonishing people not to like use a lot of shorthand in their solutions for, especially for exams. It's like it's not only bad, like using a lot of shorthand. Like I use shorthand, you know, all the time when I'm lecturing and doing discussion, but that's because I'm talking verbally to you guys, so I can explain what I mean, right? And obviously, when I talk like with words, I'm using complete sentences, and it all makes sense. So the shorthand is just like an efficient way for me to write the idea on the screen, so that we have a reference material, right? But when it comes to like a solution on a homework or an exam, really, that's where the solution is going to be read on its own and it has to like stand alone essentially, then like the solution really is like it's supposed to be your like best representative of the idea that you had for like solving the problem. And so anyway, I was going to kind of explain this, but I think there's not a whole lot in there that might necessarily be like there wouldn't be like a lot of, maybe I'll add also, I'll try to add in an element into that video about like here are some strategies you can try to follow to like help you make that like transition, because that is honestly like one of the focuses of the class, is trying to get people to bridge the gap between their like conceptual understanding and their communicative abilities. Basically, like you have to be able to communicate your ideas clearly. And it's like I genuinely believe that the better you learn to just like write clearly, like the better, yeah, the better you learn to write down your ideas clearly, the easier it'll be for you to actually like convert your intuitive ideas into an actual proof. Like those two processes are related to each other, because it's like the more you practice writing well, you're like training your mind to think in terms of like certain kinds of expressions and sentences and so on, that like those that like once you learn how to express yourself that way, you'll start like internally expressing yourself that way to yourself as you're thinking about solving the problem, and that will help you like formulate proofs once you have sort of like raw ideas basically. um, but I have some other tips actually. I mean, I have some other like problem solving strategies, so maybe I'll try to include that in a video. Yeah, thank you, that's good feedback. I mean, it's good to hear what people want. Any other questions or comments? Okay. Um, yeah, I don't think we have time for another like full-blown exercise, but I think maybe what we can do is hmm. Um, hmm. Yeah, I'm not sure. The timing's just kind of awkward. I might just end it early today by a few minutes, unless there are more questions. Maybe well, one comment I was going to make actually about this problem we just did, right? If you change the assumption here to have an open endpoint, right, then everything falls apart, right? The problem doesn't work anymore because you can't. I mean, essentially, what could be happening is basically that between 0 and k, like as you get close to the endpoint 0, right, then f might, you know, either diverge to plus or minus infinity, or it might oscillate, you know, really quickly or whatever. So it's like it's always really important to, especially when it comes to uniform continuity, or just in general, to be like very wary of open endpoints, because those are like prime targets for places where a function can like behave badly, right? So like if we were to change this to an open interval or an open endpoint, for example, then like in order to make this work, you would have to also assume if f is uniformly continuous on k infinity, and 0k, then actually now the problem becomes valid again. In fact, actually, how can you very quickly solve the new problem if you take for granted our solution of the previous version of the problem? Okay, so say we already solved the previous version of the problem where this was a closed endpoint. How can you like in one sentence solve the new version of the problem as it's stated? Like what I'm suggesting is that there's an easy way to convert the new version of the problem into the old version of the problem. Maybe there's a piece of the material you guys are kind of sleeping on. I feel like this kind of gets slept on a lot, actually. I'm not sure. I don't know if that's what's going on, but the last time I taught this class, I remember it being something that people didn't pay a lot of attention to. But remember, right? So if f is uniformly continuous on on an open interval, let's say, right? So clearly, if f is uniformly continuous on 0k with like k closed, then it's also uniformly continuous on 0k as an open interval on both sides. And we know that if it's uniformly continuous on an open interval, you can extend to both endpoints, right, continuously. So so this is like separate from everything we just did. F uniformly continuous on 0k, oops, means there exists a continuous extension f tilde to 0 infinity. And clearly f tilde is uniformly continuous on k infinity, right? So then our previous solution now applies, and you can say that f tilde is uniformly continuous on its entire domain, and then from that you can infer that f itself was uniformly continuous to start with on its entire domain. Right, any questions about that? Yeah, honestly, the extension thing is like surprisingly powerful to be able to like to remember that whenever you have a uniformly continuous function on an open interval with like a finite open endpoint, right? Like this one, 0k, right? Where 0 is like this open endpoint, you can always extend it to a continuous function. Yeah, on the closed interval. And then of course the extension on the closed interval, right, 0k, at least on 0k, it's automatically uniformly continuous because it's continuous, right? So anyway, okay, I'll leave it at that, and I'll see you guys tomorrow. Have a good evening.
Thank you.